Can you hear me? Cool. Yeah, so my name is Tyler Riccio, and my talk is going to be a gentle introduction to interpretation, bytecode, and fastcode. I actually want to say this is my first ever talk at a conference, so if you see me pass out up here, it's normal, don't worry. So my background, I'm currently a platform owner at Citizens Bank. I manage data scientists, data analyst platforms. So in like non-corporate speak, I just help run like data science tools, like specifically from the Python perspective. Our bank is evolving a lot more towards Python from some older tooling, so I've been really lucky to be a part of, like a big part of that migration, teaching people Python, like seeing how non-Python users, like if they're coming from C or from R, like are like learning about the language, and that's like really formed how I think about the language too, and I've been really lucky in that perspective. I'm kind of interested in like the medium to big data coding problems. I know that's probably a little bit niche, so hopefully there's some people like me, but in my current role and the role prior, I've been tasked with kind of these sorts of problems, and it's led me down the road to like kind of try and specialize in this area. I love the creativity it takes. Like everything is really like almost at arm's length. I love the complexity of the problem itself, and it led me from data analysis and data science to more of like the CS engineering side. Personal note, born and raised in New York, currently live in Columbus with my fiance and our 2 cats, Winston and Duchess. So first thing I want to introduce, or first concept, is what is slow? So slow, ooh, I can't even see my own slides. So slow, I think, is when the user notices. If something is slow and it's bubbling up and you are getting complaints, you're getting issues on GitHub if you're a developer, you're getting angry execs staring at a dashboard wondering why the hell the data won't load, that happens, then it's probably too slow. Second thing would be a progress bar. So if you, as the developer, need a progress bar, it's probably not too slow, but it might feel a little slow, like for your life. And if the user needs one, it's also probably too slow. Like in my experience, I've learned that users can really stomach a progress bar, but if you're getting into that territory, you might want to, interrogate what the code is actually doing and see if you can take some steps to speed it up. And the third one, which in my opinion, at least in my world, is the most important, is if you have to batch the data instead of streaming it in like live, then it's probably too slow. Like a common thing would be if you need to compute some features for like a machine learning model, and the model is of course more accurate with information gain, and let's say something changes in between now and the next batch, you're losing that information gain. And there comes a point where there's like a revenue trade-off. Like, do I need to spend more time optimizing this code, or can I just wait for the next batch? Those are like kind of when the interesting problems start to arise where, maybe you want to solve the engineering problem instead of losing that revenue. So next thing I want to cover is how do computers actually work? I think this is crucial to understanding this as a concept. So if you have a CS background, or you're a software engineer, or even a data engineer, this is definitely a review. But it's pretty novel for most of the data analysts and data scientists that work in Python, at least in my world, and especially those coming from even Excel or R, and they're coming into Python. Like this is like a topic that's not super well understood, and I think it would be really beneficial if it was easier to digest. So, as we see, oh, I hope you guys can see that. Anyways, the slides will get released, but that is basically how a computer works at a very, 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 very high level. You have your input device, so you're typing, you have your processing units, you have some memory which stores your data, and then you receive some sort of output, or some data goes back to the memory. So the first step, and again, this is incredibly high level, obviously, is your code logic or your business logic is translated into the CPU instructions. So it gets compiled or it gets interpreted, we'll get to those terms later, into machine instructions that the CPU can actually understand directly. So each instruction can be a command like, add these two numbers, load this from a memory address, just your business logic. Part two is the instructions reference data that's stored in a memory location or a memory address. So think address like literally a street address. It's just a spot where things are. So every piece of the data in your programs, variables, arrays, objects, et cetera, they all live at explicit addresses in the memory itself. So the CPU instructions can reference these objects, fetch them, and do some things with them. Do whatever you want with them, really. And part three is the CPU performs the operation itself. So this actually happens in the ALU, but oftentimes they're kind of like used in tandem. They're really very similar. The ALU is the thing that does the operation itself. That's the arithmetic logic unit. The CPU loads the data from memory. It stores it into something called like a little internal register, which is like its own mini memory. And then it does the operation, and then it's going to return that data back to the memory unit or to the output device. Output device being like maybe a terminal, a file, something. So how does Python do this? So we have our little ChatGPT generated chart here. And there's really like 3 steps to this. You have your source code, you have your bytecode, and then you have your C code. So the first part is taking the source code and turning it into the AST. The AST stands for the abstract syntax tree. So Python is going to, when you click run, Python will take your raw text and break it down into tokens. If you've attended any LLM talk, you've probably heard of tokens. So they're here too. These are like your keywords, your variables, your operators. There's some form of this in pretty much every language. And it's sort of like a tree structure of logic. It's the logic of your code. You can interact with it in Python. It's actually quite easy if you use the AST module. Part 2 is the PVM interprets the bytecode. If you've been around Python long enough, you've definitely heard of bytecode. And just very simply put, it's like a lower level, platform independent set of instructions that's not source code. You can read it. It's not unreadable, but it's definitely not looking like Python code. And then this gets sent to the PVM, or the Python virtual machine, which is like another processing unit that runs your, did I go down? Okay, here I am. That's interesting. So the PVM is an additional unit that figures out what's going on in the bytecode line by line. It says, what do I actually need to do here? Part 3 is the code leaves the PVM, and it's dispatched to C. So I'm just assuming we're using CPython here. I don't want to speak to any offshoots. And the real computation happens in step 3. This is your math. This is your file I/O. This is your memory management. Everything is happening in optimized C under the hood. And I think the main takeaway here is that Python doesn't do a lot of this work itself when it comes to computation. It is a phenomenal orchestrator. It orchestrates all of this code into, and it dispatches it down to, I have no clue why that keeps happening. Sorry. But it dispatches a lot of the logic down to either C, if you're using CPython. We're going to talk about extensions like Rust, if you're using like a Rust module. And that's really where the heavy lifting is going on. Okay. So this all comes with a set of problems. Unfortunately, the problems are the things we love about Python, but it's the things that make it slow. So the first main issue, and there are plenty of issues, but I'm just want to break it down into 3, is the dynamic typing. Dynamic typing is awesome. Dynamic typing is probably a reason maybe 50% of us are even standing in this room. It's certainly the reason I'm up here. There's a performance trade-off. When you perform an operation, say like x plus y, Python has to check, obviously what type of x is there and what type of y is it. If one is a float and one is an int, what type of floats and ints? Like, are they float 128? Are they float 64? What if you add 1 to a Boolean? You can kind of do that in Python. You can do all sorts of crazy stuff in Python that you can't easily pull off in other languages. So every time the interpreter has to figure out, what type you're dealing with, that's a ton of overhead. And then you think in a loop, this is happening per iteration. So the CPU is spending a lot more time figuring out, what's going on than doing a lot of the computation. Second part would be the no vectorization problem. So vectorization, like really simply put, is just taking a whole sequence of elements and operating on it at one time, usually with something called SIMD, which is like single instruction, multiple data. So if we think back to the CPU instructions, we can kind of dumb down, it's really not a single instruction, but you can dumb down the number of instructions and cycles needed by the CPU if you're using something called these SIMD registers, which other language has easier access to. So for loops in Python are going to go one element of the time. It's going to go line by line, enter that interpretation loop. For each item, look at the bytecode, or generate the bytecode, send it to the PVM, dispatch it to C, and then the C is also like fairly complicated because it has to do a lot of this branching to figure out, what are the types? Can you even do this operation? Is this an error? And so on. The third part is the branch prediction problems. Branch prediction is like a little known element of CPUs, at least when I'm dealing with a lot of analysts. Like every time I explain the concept of a branch predictor, you're like, oh my gosh, that's like so cool in the hardware. I never knew about that. But the branch predictor is an element of the CPU that tries to prefetch instructions, data, among other things, when it thinks it knows what the next step is. So if you think in a really tight for loop in a low-level language, you can like fairly easily predict what the next step is because you're just iterating over, I don't know, 1 million elements, 2 million elements. You're doing 1 million things in a row. When you're doing this in Python, you're actually just entering the interpretation loop 1 million times. And that interpretation loop is so many instructions, the CPU can't reasonably guess what the next instruction is. So other languages have access to these branch predicting these branch predicting optimizations that Python, because it's interpreted, just doesn't really have great access to. So all of these steps, at the end of the day, they just increase the number of interpretation steps and the amount of work it takes just to perform the computation itself. So I do want to run through a really quick example. So each sublist, I just given a sequence of sequences, sum the subsequence. So I'm not going to get into the nitty-gritty of benchmarks, like that's a whole discourse. I'm going to keep the timing really high level. But this is sort of how I would do this, in a pure Python example. And it took my machine. Huh? Oh, bigger. Oh, boy. I don't know. Anyone know? Here? There we go. Sorry about that. Is that better? Cool. Let me get back here. Okay. So yeah, on my machine, I just have a Mac M1. This took about 109 seconds, which is actually pretty fast. If we were to do this in NumPy, this is kind of how I would do it, also pretty easy. So using that NumPy function, that was 3.4 seconds. So that's obviously a huge speed up. So when you think about what NumPy just uses direct C calls. So it's a lot stricter. You basically have to call these pre-built functions that are optimized to be static. You kind of lose the freedom of Python syntax, but you pick up the speed. It's just at the cost of this flexibility. So now I'll go through those 3 problems before. Dynamic typing, how does NumPy solve that? So NumPy arrays are statically typed. It doesn't have to check all the data types for each element. It knows what every single one of them is. Along with some other optimizations, this eliminates the overhead of type checking at runtime that you're going to get with a Python sequence. Not all Python sequences, though, like almost all of them. But the interpreter knows exactly how much memory each element needs, and it can optimize accordingly. It doesn't have to check the type. It knows where it is, among other things. NumPy is really a phenomenal. I can't summarize the whole library in 3 minutes, but it's really a phenomenal library. The second part would be vectorization. NumPy can operate on the whole array. So instead of looping through elements NumPy 1, at a high-level interpretation loop, NumPy can send the entire array down to C itself. So it reduces drastically the number of instructions that the computer needs to actually do your calculation, because it's doing it at a much lower level. So the loop is happening in optimized C code rather than an interpretation loop that would be happening in high-level Python. Now the branch predictor. So like I said, NumPy is an optimized C code, and the creators of NumPy thought about this. They know about the branch prediction problem. They know how to optimize the CPU. The C compiler knows how to optimize for these things. And there are all these aggressive optimizations and like slow evolutions of algorithms in NumPy that know about all of this that we just don't have access to in Python. And this is why the branch prediction problem is like really elegantly solved because everything is so tight in C, the CPU has a very easy time predicting what the next step is. Using Numba, which is another Python framework, it's just a JIT compiler. It's 4.1 seconds, which is also very fast. So very quickly, JIT compiler basically takes the Python code, turns it into machine code before it runs, then rather than interpreting it line by line, gives you kind of the speed of compiled languages while keeping the flexibility of writing in Python. There's no real Python code getting run. If you think about that second step where the bytecode is interpreted by the PVM, it's actually not even getting to that step. It's going to something else called LLVM, which is kind of like skipping a few steps and going down to low-level code. So it fixes the dynamic typing problem because the types are fixed at runtime. By the time the function is running, Numba is figuring out what the types are, and let's say you pass like a sequence of 100 integers. By the time you get to integer 50, Numba already knows that, or it's really LLVM, Numba already knows that the rest of the integers are almost definitely, the rest of the elements are almost definitely going to be integers. So it knows, okay, we can optimize for the integer hop path. Or we can take this optimization that we only have access to in low-level code. We have the vectorization problem. So Numba will auto-vectorize if possible. So because of its backend, it can automatically detect loops, and it can vectorize and convert them to those SIMD instructions, as I said before. So if you have a simple for loop over arrays, Numba might look at that, and during the runtime of the function, it might stop and just hoist that into a single vector instruction, because it can modify your code while it's running, take all these little optimizations during runtime. And if we look at branch prediction, if we look at the branch prediction problem, NumPy can apply these compiler optimizations on the fly. So if we go back to like that integer problem, if you have a sequence of elements, and by the time you get to element 50, Numba can look and say, we know these are integers at this point, so let's assume that they're integers, and let's send them to the CPU, and we can allow the CPU to prefetch integer instructions. We don't have to guess whether this is like an int16, an int32. We can use the past history of this function, and we can predict what's coming in the future. So what you see is you end up seeing, as the function goes on, these aggressive branch prediction optimizations. I actually had an example of this at work where I had an hour-long function. I had a progress bar. I know I broke my own rules. And I was seeing the number of iterations per second. And by the time the loop had gone on, like I think it started off at 20,000 iterations per second. And I look back 40 minutes later, and it's at 200,000. And it's just, you see it slowly going up as Numba is figuring out smarter ways to optimize this code. Okay. See, it keeps going out. So the third thing I want to talk about is polars. So polars ran this code in 15 seconds. So a little bit longer than NumPy and Numba, but definitely less than the 109 seconds or so that the pure Python loop would have taken. So polars is pretty similar to NumPy. It's like a DSL. It's almost like a domain-specific language. It's got like a world of syntax to its own. And you're not actually calling much Python. It's basically asking you to like fill out forms, and then it sends that logic off to Rust. So if you think of like NumPy and Numba, the common theme is we're kind of skipping the whole bytecode thing, and then we're kind of jumping right to the C code, and it's like a smaller subset of the C code. Polars is written in Rust, but you can think of them really similar. So again, you lose the flexibility, but you buy back so much speed. So if we want to think about the typing, polars has really static types. Like they're very strict about their typing. So before your code even runs, it knows what the types are. So where you have a pure NumPy loop, you would have, for each element, again, got to do the same thing. What is this? Is it an integer? Et cetera, et cetera. We already know that beforehand with polars. We can just throw all of that type checking pretty much to the side. There is some lower level type checking, but it figures all of that out for you. If we think about vectorization, polars is vectorization by principle. By definition, it's a vectorized query engine. It will always operate on the whole column at the same time. So it's not even like, oh, we do this because it's fast. It's like a philosophy of how the query engine was written. So, with that, it's like a core architectural approach, and so many decisions are built around, like every operation has to be done vectorized or else we won't do it. If you're working with like a lot of data, like if you're a data engineer, a data scientist, data analyst, this comes in really clutch. It's extremely helpful. And the third part is branch prediction. So polars, and the creators talk about this a lot, they optimize for modern CPU architecture with features that are like cache friendly, and they do SIMD instructions, and they explicitly say like with the code that we're running, we're thinking about the branch predictor. This is part of what happens with vectorization, where kind of the point of vectorization is it's easy for the CPU to understand because you're sending the whole thing at the same time. It's really consistent. It's really easy to guess the next step. The next step is probably the next element in the vector. Whereas, again, with Python, you have to go through the interpretation loop yet again. This is how I did it in polars. Pretty succinct. So I do want to say, I know I'm running out of time, there's a bit of a cult of performance that I do actually want to reject. At the end of the day, it's unlikely you have to make this trade-off a lot. In my experience, you only need to take evasive maneuvers like a few times if that dashboard is really that slow, if your model is really just getting killed by the accuracy. But you're doing this typically, maybe not in this example, at the expense of the reading experience. If you can't read your code at the end of the day and make edits to the business logic, what's the point? So I think that's something like you really should keep in mind. And I come back to this as the Instagram problem. You can spend 10 minutes optimizing your code, or you can wait the 10 minutes, scroll on Instagram, and it's done, and you have your result set. So if you can make that trade-off consistently, I would probably just sit there and scroll on Instagram, or at least that's what I try to do. If this is in a production setting, obviously it's very different. But I just want to emphasize, this is not one size fits all. This is for if you're really struggling with problems. And we're definitely at time, but I have to, there we go. This will get attached in the slide, but there are some really great recommendations on, how all of this stuff works in depth. All of this stuff works in depth. Polars, the creators talk about how they took their architecture choices. They talk about all of this and more. They explain it 1,000 times better than you'll hear me explain it. The second one is an excellent book on how Python interacts with the computer, among other things. It really makes this stuff, at least when I was a data scientist, that really connected with me for whatever reason. And then on the bottom, there's a primer on vectorized query engines. If you ever heard of DuckDB, it's also a similar thing. Things are kind of moving probably towards that direction if you keep up with database stuff. Yeah, I think that's it. Yeah, I can do questions.
So if there are any questions, the speaker would like to take questions. Anyone?
I actually purposefully left that out. I'll post my code with GitHub, like how to run the benchmarks soon. I have a comment saying like I'm not even going to touch that. But, oh, sorry. Yeah. So the question was about single-threaded versus multi-threaded, like it was an open question. So NumPy is single-threaded as of now. There are some ways to like kind of get around that, but usually with vectorization, that kind of goes hand in hand. It tends to be very easy to parallelize vector code because you're operating on the whole thing. Like there's not like a random break in between it where you have to coordinate with like a master node or anything like that. So I think that makes it easier for things like Polars. Like Polars uses all of the CPU. Numba can take advantage of all of the CPU. And then, is the question related to like Python itself or? Yeah, I mean, obviously I think we're gonna see that change possibly. Like maybe it's a little bit farther out, but that's obviously a performance issue. Like I can only speak from experience. Even when you're doing multiprocessing or trying to like get around the GIL, the results are not as fruitful as you like might expect with like a engine that will do this natively, like Polars or like Numba. But hopefully that's going to change. I would love to see a world where Python blows all of this out of the water and it can like take advantage of these optimizations. Like obviously the JIT compiler is coming, and you can. There's a good JIT compiler talk on PyCon where they talk about like the type checking problem specifically. Like what if we were able to do what Numba does and like patch some of these types like halfway through the loop. So it's cool that like they're focusing on that. Maybe that's where Python could win in the future, but I'm almost more optimistic on the JIT compiler than the parallelize part of it for some reason. Might just be it's all a bit of a mystery, you know. Two more? Sorry.
Yeah, we still have time for one more question. If there are no questions, thank you very much. Round of applause.